Welcome to this chapter. This is an introduction to radioactive decay. There are two basic types of radioactive decay. The first one is the alpha decay, which means that the nucleus will emit an alpha particle which is composed of 2 protons and 2 neutrons. This is the nucleus of the helium atom. As we already mentioned, this type of nuclear decay is mostly due to the proton-proton repulsion in very heavy nuclides, which cannot be overcompensated by the high number of neutrons. This alpha particle is a heavily destructive particle, and I show you that this is mostly used in therapy in nuclear medicine. Please note that when we talk about nuclear medicine, it means that the radioactive nuclide is incorporated in your body. And this is the situation where an alpha emitter is very dangerous, and that's why I put here an exclamation mark. So a medical doctor should be extremely careful when he or she decides using alpha particles for some therapy. The second type of decay, which is actually the most abundant type of radioactive decay, is the beta decay. Because this can be found at any atomic number or mass number. As you remember, there is a second parameter of the nuclear stability is that the proton to neutron ratio should be optimal. If this is not optimal, if we have more neutrons than needed, then we have the negative beta decay. When you have negative beta decay, the mass number does not change, but the atomic number will increase by 1. And you see an electron emission plus a so-called antineutrino, which is a very elusive particle. You don't have to care about that because it is even extremely hard to detect. So it causes no danger, and it is not possible to use it in medical purpose. So, however, the electron, once it forms in a tissue, it has also a destructive power, not so destructive as the alpha particle, and still it is used for therapy. Once you have too many protons as compared to the number of neutrons in an optimal neutron to proton ratio, then you have the positive beta decay. In the positive beta decay, you have a positron emission and a neutrino. Once again, you can safely forget the neutrino. However, you have a positron, which is an antiparticle. And once the positron encounters an electron, then you will have a so-called annihilation radiation. That means that the electron and the positron will disappear, and you will have 2 gamma quanta, actually gamma radiation. And as we will learn later, gamma radiation is very good to use for diagnostics purpose. So that's why this type of decay, so the positive beta decay, will be used for diagnostics. When you have electron capture, just look at this. The starting nucleus and the resultant nucleus is the same here and here. So it is actually very interesting. And here you have no particles emitted which can be detected. So as I said, the antineutrino is extremely difficult to detect, so it is actually useless for us. Then how can you use it for diagnostics? The truth is that once you have this electron capture, that means that an atomic electron will be absorbed by the nucleus, in the nucleus. Therefore, if you have one missing electron from one of the electron shells of the atom, then this electron vacancy will be filled from another shell by another electron, and when that happens, you will have an emission of so-called characteristic X-rays, and these X-rays can be detected, and that's why such type of nuclides can be used for diagnostics. This is not a third type of nuclear radioactive decay, because the situation is that once you have alpha decay or beta decay, most probably the resultant nucleus is not a ground state nucleus, it is excited. And once this excitation disappears, so the excitation occurs, then there is an emission of a gamma quantum. And this gamma quantum can be easily used for diagnostics. This is a summary chart of the different types of radioactive decays. You see the color codes here. The black one means the stable nuclides, the nuclei. The blue is the positive beta decay. That's where we have an excess protons. And the magenta color is for the negative beta decay. That's where we have too many neutrons. You see here the magic numbers I already mentioned, and it is interesting to go up to here. This 82 is actually for the lead, and there is only one more element which is still stable, that is the bismuth I already mentioned. We have alpha decay typically for very heavy nuclei, you see, and as I said, they are very seldom used for therapy, but we will see later an example for that. The other types of decays are not really important in the medical practice. Let me say some words about the rate of the radioactive decay. So the question is that how fast it is. If you want to describe this mathematically, then you see an exponential function. So this is the starting number of nuclides, and this is the number of nuclides after time t. And this lambda is the so-called decay constant. If you are not familiar with the exponential function, just don't worry. The point is that from this decay constant, we can calculate the so-called half-life. The half-life is the time in which the activity of the radionuclide drops to its half. So it is very easy to calculate the activity at any time. That means, say, if one half-life elapsed, then you know that the original activity dropped to 1/2. If another half-life elapses, then the original activity will drop to 1/4 of the original activity. So this is so simple. Why it is important for us is simple. If you use a radionuclide in medical practice, then you are not interested to have a long-lived isotope, because if it is a long-lived isotope, so it has a long half-life, then you will expose your patient to radioactivity for a too long time. So you need this radioactivity only for the duration of the medical treatment. That means maybe half an hour, 1 hour, or something like that. So the preferred half-life for radioisotopes used in medical practice is maybe a few hours or a few days.